pulmonary ventilation is referring to the inspiration and expiration of air. But there's a lot that goes into that pulmonary ventilation. It's not just simply breathe in and breathe out. It's a mechanical process that deals with your volume changes of your lungs. Saying volume changes, well, yeah, your lungs expand and contract. So they're changing the volume of the lungs. And that volume change, that's going to help with the breathing process. Because as the volume changes, the pressure changes. And those pressure changes are what move the air in and out of your lungs. Because as the pressure drops in your lungs, it becomes lower. Well, it's lower than atmospheric, so the air flows in. But if the pressure inside your lungs goes up, you have a higher pressure inside, air comes out. The goal is to try and reach equilibrium. So as you change the internal pressure inside your lungs, the air is flowing in or out to reach the equilibrium state. And that's where Boyle's law comes in. Now, Boyle's law is dealing with the relation of pressure and volume. So if you look at the first one here, if you're going to increase the volume, if you increase volume of a sealed environment, the pressure inside decreases, gets smaller. But if you're going to make the volume smaller of a sealed environment, the pressure inside goes up, gets higher. So you end up with this P1 V1 equals P2 V2. Basically, pressure is working inversely with volume. So looking at the idea of pressure equals 1 over volume. So pressure equals 1 over volume. So as the pressure goes up, volume goes down. If the pressure goes down, volume goes up. Or we can look at the other way. Volume goes up, pressure goes down. Volume goes down, pressure goes up. Now let's think about that in relation to the lungs. If you're breathing in, think about your lungs. What happens? The lungs get larger. As the lungs get larger, the volume increased. If the volume increases, the pressure decreases. That means you have a low pressure environment in your lungs now. Air flows in because you're trying to reach equilibrium. But if you're breathing out, the lungs get smaller. Smaller space, smaller volume means higher pressure. Pressure is higher inside, air flows out to try and reach equilibrium. So we're looking at breathing, the inspiration, expiration, all based on pressure gradients. The relation of volume, lung volume, to pressure. So lung volume increases, pressure goes down. Lung volume decreases, pressure goes up. I'm going to throw this up full screen because I want to make sure you can see exactly what's coming up on here. So we'll start with the inspiratory muscles. Think diaphragm. Think the intercostals. But we'll stick with just the diaphragm, just basic, simple breathing, everyday breathing. Basically what happens here now is the diaphragm itself is contracting. As the diaphragm contracts, that means it's going from a dome shape to flat. That's going to increase your thoracic volume. Your lungs get bigger. By increasing the thoracic volume, the intrapulmonary volume is increasing. So the inside of the lungs are getting bigger. This results in the intrapulmonary pressure dropping by 1 millimeter mercury. So -1 goes down by 1. Because a little bit larger volume means a little bit lower pressure. That lower pressure means that the air was flowing into the lungs to try and reach equilibrium. The air will flow in until you have equilibrium, until the pressure difference is 0. Now that's inhalation, just a regular basic inhalation. Keeping this full screen for a second, let's go the other way around, expiration. Now in expiration, those muscles, those inspiratory muscles, think the diaphragm, it's going to relax. That means instead of being flat, it goes back to its relaxed dome shape. By going back to the relaxed dome shape, then your thoracic volume is decreasing. That means that the lungs are getting smaller. The elastic recoil is happening passively. There's no active, you have to put energy in. The lungs want to recoil, which means that the intrapulmonary pressure, the pressure inside the alveoli, is now a +1. It went up by 1 millimeter of mercury. Because as the lungs got smaller, the volume decreased, the pressure increased. Which means that the air is flowing out of the lungs. You're trying to reach equilibrium. So it's going from the high pressure inside the lungs to low pressure in the environment around. That means that we're looking at breathing, inhalation and exhalation, based on volume changes, which cause a pressure change, and you create a pressure gradient. Now, the deeper your inhalation, or the more forcibly you exhale, the speed changes, which means you need a higher gradient. The higher the gradient, the faster the airflow. Think about if you're looking at a creek and it has a little 1-foot drop. The water goes 1 speed. But if you have a 10-foot drop, that water is going a lot faster in the bottom because there's more of a gradient difference. So you want to make sure that you're looking at the gradient of the atmospheric pressure versus the intrapulmonary pressure. The larger the difference, the faster the airflow. So if you're breathing very deeply and very quickly, you're doing that by generating a larger volume difference, which means you have a larger pressure difference. Now this one, looking at 3 different things here. Up top, that's the intrapulmonary pressure. The next one down is the intrapleural pressure. Now we know the difference between the intrapulmonary pressure and the intrapleural pressure is the transpulmonary pressure, and that better be negative. The third thing is this volume of breath. You'll notice the volume of breath, it just goes up, but it comes back down. Sure, you breathe in, you breathe out. Whew. So basically, your breath, you're increasing the amount of air goes in, and the same amount of air is heading back out. Now this is showing 0.5 liters, 500 milliliters. That's a typical, or kind of what they said, the typical normal breath. Now sure, everyone breathes differently, but when we say the typical tidal volume or typical breath, we're referring to 500 milliliters. So if we're looking at these, notice you start breathing in. Watch what happens to the pressures above it. The intrapulmonary pressure starts to go down. But then before you finish the breath, it goes back up. Because that inhalation, you pause at the top. That's when you've reached equilibrium. And then you start to exhale. Notice the pressure went up because the volume went down. And the same curve. Because the end of the exhale, you pause and you're back at 0. But then notice the intrapleural pressure. This intrapleural pressure didn't have that same curve. Instead, it simply goes down, -4 to -6. Then it simply goes back up, -6 to -4. That's because as you breathe in, your lungs get larger, larger, larger. The largest point of your lungs for that breath better have the most recoil force going back. So the largest difference will be when the lungs are the largest capacity, which means your transpulmonary pressure also is on the larger side at that point. So looking at intrapulmonary pressure, which mimics the actual amount of air going in, so the volume, and then the intrapleural pressure, which is based on the recoil force of the lungs. Together, they keep that actual transpulmonary pressure negative. Just the negative amount fluctuates. The higher, the more negative it is, the larger your lungs are. The less negative, the more collapsed your lungs are. And when I say collapsed, I mean back to normal, not collapsed down, just back to normal breathing. So looking at the physical factors that can influence pulmonary ventilation. Now, these are things that can all play a part with all that pressure we just talked about. So again, there's a lot of pieces coming together here. So these are things that can hinder the airflow. First off is airway resistance. Now, airway resistance, we're talking about the trachea, the pharynx, the bronchi, the bronchioles. If there's any resistance inside those tubes, maybe there's extra mucus or one's collapsed, that can impact how the air gets into the alveoli. The more resistance, the harder it is to get the air down. Alveolar surface tension. Now, I mentioned surfactant in a previous video. Surfactant helps to reduce the surface tension. But sometimes there isn't enough surfactant, or there's too much mucus just kind of on water droplets overpowering it. So if you increase surface tension inside the alveoli, that's going to impact how much oxygen can be absorbed because it starts to collapse or block areas off. And then lung compliance. I've up down here distensibility of the lungs. The idea is lung compliance is how flexible are the lungs. If there's sometimes disorders or there's a lot of pollution in the air over decades of time or smoking or anything that can change the physical structure of the lungs so they don't stretch as easily or don't come back as easily, that can impact the pulmonary ventilation. Because if you breathe in and you're breathing out, but your lungs aren't recoiling as they should, that slows the whole process down and makes it harder for the proper exchange of gases. So 3 different things, for example, that can all play a part in how this pulmonary ventilation is working. So a little bit about some of the ideas of how this whole exchange is working. Still have more to go, but idea of pressures and exchanges back and forth.